Hi everyone, Peter here from Lucid Motors again with another tech talk. And today there's a palpable sense of excitement here because this is the tech talk that I know so many of you have been long waiting for. Because we're going to go deep into the heart of our Lucid integrated drive unit here, right to its very core, and explore the inner workings of the Lucid electric motor. A motor which just weighs around 67 pounds, and yet is capable of generating 670 horsepower. Yes, about 10 horsepower per pound, and yet blends that with extraordinary, unparalleled efficiency. How was this even possible? We're going to delve right into the technology of that motor, how it was conceived, how it was analysed, how it was developed, and what makes it so very special. We're going to take you through that journey, and then I'm going to introduce the concept, this crazy concept of the zero mass drive unit. Is that a fantasy? Is it something that might happen in the future? Or the craziest notion of all, is it even here in production today? So before we get deep into the motor, let's take a look at this integrated drive unit, the Lucid drive unit. It comprises 4 discrete elements. Inverter here, with a motor section beneath, reduction gear sets, and differential. Those are the 4 elements. Collectively, this comprises 74 kilos. But the motor itself is around 31 kilos, just over 67 pounds. Now, to really enhance one's understanding of the performance of this motor, I want to cover just 1 or 2 key principles, starting with what's the difference and relationship between torque and power. So, armed with a great torque wrench, let's explore torque. So, here we are with the torque wrench. Let's apply a torque to this wheel nut on a Lucid Air. And what am I doing? I'm pushing down here with my right hand, supporting with my left. I'm applying a force multiplied by a distance. Force times distance, that defines what torque is. And we can measure that a couple of ways. We can measure it with pounds-feet or by Newton meters. And here's an interesting little relationship. 1 Newton meter equals 0.7376 pounds-feet. And a good way of remembering that is just to think of a 737 aircraft. It's pretty close. Now, that 0.7376 is also tantalizingly close to 0.75. So a simple way of doing the math in your head is to think of a Newton meter as about 3/4 of a pound-foot, or very close to that. And conversely, a pound-foot is about 1 1/3 Newton meters. But they're all just measurements of simple torque, force times distance. Now I hear some of you saying, oh, but if we're going to use this to demonstrate the torque from an electric motor, surely that's going to apply to the centre here of the wheel. Well, strangely, mathematically, it doesn't matter. You can apply a torque to an independent position within the free body of the wheel. It doesn't actually matter in terms of where the interface forces, how they resolve out. And in this case, we have the forces at the tyre contact patch and the bolted connection to the hub and the brake disc. So now, armed with that information that torque is just force times distance, let's develop that into a relationship with power in the context of an electric motor. So, we've learnt that torque is just a force times a distance. And we can just write this down. Torque equals a force, that will be in newtons, times a distance, and that will be in meters, a distance x. And that's all it is. I'll just make that simpler. Torque equals Fx. Now, here's a crazy observation, that the units for torque force times distance, those who may have seen my previous Tech Talk on batteries will recognise force times the distance is something else. It's actually energy. So how can torque be the same units as energy? There's a crazy construct here because there's no movement in that torque and there's no energy taking place because there's no displacement. But force times distance is energy. And you may remember me lifting the apple, which weighs about 1 Newton, about 1/10 of a kilo. And if I lift that exactly 1 meter up, that's force times distance, that's 1 joule. And so this leads to this core construct that we can have an energy equivalence of a torque. Let me explain that with another little prop that I've got. So here we have a representation of how a torque could be applied to a disc. Imagine the torque being applied this way, and the force is being applied at the outside of the disc here, and it's been applied across this distance x, which is shown by this piece of string, right? So that's torque, force times distance. But we've also seen that force times distance is energy. So what if we consider this a completely different way? What if we applied a force around the edge of this circumference through this same distance through this piece of string? The force then would go along this arc, and it would start at a point here, and it would end up at a point here. And the force would travel all this way. That force times that distance, x. And when we get to this point here, we see an angle has been subtended. And this angle we're going to call theta. And we define that by a radian. So a force times a radian is a unit of energy. And we know that energy divided by time is power. So if we can do this force through this distance in a set amount of time, that will define power. And we have a great analogy here because we know that in a linear sense, power equals energy divided by time. And that's in a straight line. And from this we can derive that rotational power, this is straight line power, this is rotational power, equals torque times angular velocity, which we will show as theta dot. That's effectively the energy equivalence linking power with torque through the angular velocity in radians. Now, there's a great similarity and synergy here between the relationship between power and energy, and from that we derive that power in a straight line is force times velocity. And these are key relationships. In a linear relationship, power is force times velocity. And in a rotational context, power is torque times angular velocity in radians per second. So wait a minute, I hear some of you cry foul here. Who measures rotational speeds in radians per second? Only engineers. We really all talk about revs per minute. So how do we get revs per minute into this formula? That's crucial. Now, we can do that very easily because if we think of 1 radian per second, the one complete revolution going all the way around there is actually 2 pi radians. Pi is just over 3.14, so 2 pi is just over 6. So it would take us 6 seconds to go 1 rev if we're doing just 1 radian per second. And that 6 seconds is 1/10 of a minute. So 1 radian per second is very close to, not quite, I think it's about 9.56 RPM, but it's very close for doing simple mental arithmetic to about 10 RPM. And then we can do some really fascinating math here. Just imagine if you've got a motor that's capable of a thumping 500 Newton meters. And imagine if that could create that torque at a crazy 10,000 RPM. Well, actually, armed with this new information, that 10 RPM is about 1 radian per second, we can say the power equals the 500, which is the torque, times 10,000 divided by 10. Well, those 10s cancel each other out. The triple naught, that's 1,000, that could be a kilo. So the power in this case is 500 kilowatts. The math is so simple. That's about 670 horsepower. Just do mental arithmetic. Divide thousands of RPMs by 10, and you can instantly compute in mental arithmetic Newton meters into power in terms of kilowatts. Now let's develop that theory to the next level. So now, remember that power equals torque times angular velocity, effectively times RPM. What if we plotted this out on a graph? What would that show us? We can plot torque on this axis here and angular velocity, or RPM, on this axis. Because power equals torque times revs, what would an equal power line look like on this graph? It would look like a contour map of a mountain. So let's take a point to start with. That amount of torque and that number of revs. So if we double the number of revs, which would bring us out to about here, we would half the torque, wouldn't we? So we'd have a point around there. Conversely, if we half the number of revs, we get to a point about here, we double the torque and get to a point like that, and so on and so forth. And this way, we can generate a curve, which is a curve of constant power on this torque versus revs graph. And so on and so forth. That can go right up there, and we can extrapolate this line right out there. That's a line of constant power, an iso power line. Now, what if we were using this in the context of designing an electric motor? What if we were limited by the fundamental ability of the motor to generate a maximum torque? Well, that would mean there would be a natural cut-off line determined by the maximum torque. And what if we had a natural physical limit of the ability of that motor to spin? Because remember, we're going to have centrifugal forces, and those are a function of revs squared. So they take off exponentially. Double the revs, you quadruple the forces, the propensity of that motor to explode. And so then you could create a cutoff line here, where that would be your maximum number of revs. And as a consequence, what we get is this classic shape here. We get this classic envelope that defines electric motors, the electric motor performance envelope. And this is the operational area that the motor is capable of operating in. This line defines maximum torque from the physical properties of the motor. This defines the maximum power available, and that's in an electric car, it's a function of many things, often battery limited actually, and this is the limit of the motor's ability to spin. Now, there's another thing that goes on here altogether, and that is the efficiency. And we can create a contour map of different levels of efficiency within that envelope and overlay that, and that's even more important. So what are we looking for in an electric motor? What are the key attributes that we need to chase down in designing from scratch a Lucid electric motor? Well, of course, we'd like to have great power, but you can always have more power if you increase the size of the thing. We want great power density, volumetric power density, because we need the space concept to work. We need to shrink wrap the size and shape of the motors. We want to push this power out to another line of constant power out here, or even more. These are lines, ISO power lines. You know, this is P1, P2, P3. We want to move that envelope out in that direction. What else do we want to do? Well, those who know a little bit about electric motors tend to be over-obsessed with torque. And I've actually rather controversially and playfully stated I'm not so interested in the maximum torque of an electric motor. Why is that? Well, what matters is the torque applied to the wheels of the car, not the torque generated by the motor itself. And to that aim, I can use a gear ratio, a transmission, to adjust the torque available at the wheels. By multiplying the ratio by a factor of 2, I can move that maximum torque, I can double it. So the gear ratio would mean that this operational envelope in orange would come right up to here to a torque which is double, but that comes at a price. And because the gearbox has a little bit of inefficiency, so we're always going to lose a little bit of power, so this is going to be a little bit less power. But if we double the torque with a 2-to-1 ratio, we'll actually halve the actual maximum velocity, the angular velocity of the system. So we'll create this orange envelope, which represents the torque and angular velocity envelope at the wheel with a 2-to-1 gear ratio. You see that we can have infinite control of torque available at the wheel, independent of the torque available generated at the motor. But it's always at the price of the velocity. We can actually, in theory, we never do this, but you could overdrive a motor. Overdrive is often used with gasoline transmission systems. If we were to overdrive this system, conversely, in theory, we could create an operational envelope 2-to-1 of torque available at the wheel, and that would look like that green line, just theoretically. But the point is, what really matters here is not torque alone. It's the bandwidth and stretch between torque available at the motor and its ability to spin, the high-end spin speed of this operational envelope, that stretch, that very bandwidth, which is absolutely key. It's the combination of torque and ability to spin. We want to push that torque limit up, at the same time pushing that rev limit out. That is absolutely fundamental. Not torque in its own right, but that stretch, that bandwidth, that is key attribute of an electric motor. And then finally, I get back to this contour map here of efficiencies. And it's not just the absolute value of efficiency here, because a lot of traditional electric motors are pretty damned efficiency. How are we going to really make a big stride forward on motor efficiency? It's not just the numbers, but it's the area of high efficiency values that we get in the high 90s here around this point, dropping off. But then we can use the transmission system to further enhance that. So we actually use this a highly efficient zone of operation of the motor to best effect through the duty cycle of the vehicle in operation. So it was one thing to have all these great ideas, the understanding of the core principles, a vision to make a more advanced, more efficient, more power-dense electric motor than ever before. Unfortunately, it was quite another to find the expertise to actually undertake this, to make this a material reality. And many years ago, when we were still at TIVA, I had the pleasure of meeting this gentleman, Dr. Emad Dlala, Vice President of Powertrain here. Emad,
hey, Peter. Yeah.
Do you recall when we...
I recall it our first meeting by this diagram.
Oh, really?
This is how I connect our...
Really?
Yes, exact. It was an interview question, of course, and you had always the vision of improving and extending the envelope of the motor through revs and torque and power as a system.
Yeah.
And how we improve power density and efficiency was the mission.
Exactly. So the two core tenets of undertaking this mission, Emad, were one, using really deep computer simulation, going back to the laws of physics in your analysis, electromagnetism, thermodynamics, all of that and more. And then the other thing was taking a big picture view, holistic system level. For example, looking at the motor and transmission holistically as a single inertial rotational system.
Absolutely, Peter. And frankly, that what actually made the difference is that system view. Because looking at a component at a solo, you can design the best motor for what? It has to be for the system.
Exactly. This is the fun part now. We're going to get down to the nitty-gritty. This is the stator of the motor. This is the main housing. And as its name suggests, it doesn't move. It's static.
Yeah, it's a stationary. It is typically connected to a housing and then to the chassis of the vehicle. And that's why it's called stator.
OK. Now, the main role of this is to create a rotating electromagnetic field.
Correct. Yeah, so the idea, of course, to have two interactive parts, stator and rotor.
The rotor goes through here.
Yes.
Yeah.
The stator would be the one responsible for that magnetic field rotation, which would rotate the rotor with it.
So this is the intelligent part of the system where you've got the field going around and the speed that rotates determining the speed that the motor spins and how fast the car goes.
All the intelligence related to the control of the torque and the speed is done through the stator. However, the rotor plays a huge role in the torque.
Oh, of course. Yes, exactly. Now, we've got a real consistent feature here through here. We have all these slots with these copper wires running through. How many slots have we got here?
Excellent. So we have here one set of the lamination to
show. This is how it's made?
Yeah.
So we've got like a couple of hundred of them here to make this
is about 440 laminations.
As much as that?
They are 0.25 millimeters.
Right, right. So we stack all these up and you can see the slots here?
Absolutely. So these are the slots are made of 72 slots. Don't look at the small slots. We'll come back to that later.
Those are
the
crucial.
large ones are basically the copper slots.
So the copper runs through here. We've got one here ready, actually. Let me look at this one here.
Uh-huh.
There we are. Look, you see the slots with the copper.
So you have this stack, and we have this, what we call a copper right now coil. This copper coil is to construct a pair of poles. So you have the south and north pole. So you have a current flowing from one direction and goes to the other direction.
And this is a 6-pole motor, isn't it?
So this is 6-pole. That's why you see 3 pole pairs.
And of course, a multiple of 6 becomes 72.
Yeah. So if you think about it, 72 slots divided by 6, divided by 3 is actually 4, which means that each phase is actually distributed in 4 slots.
3 phases.
So that's a part of how we smooth the torque and the air gap to generate a more refined torque generation.
Now, what you've done here is something very special. The way you fill those slots with the copper. Show me the traditional way and what's different about this.
Yeah. So there are multiple approaches. So the traditional way, Peter, to do it is to create a slot, kind of round shape, and now we're going to fill it with the filamentary small stranded wires.
Round wires?
Round wires all around here.
And this is the way things have been done for the last 100 years?
Yeah, 100 years, and today it's still used. The reasons why it's common, because it can be handmade.
Yes.
And it started manually back
Right,
then how
right,
to
of
do it
course,
because
yes.
it's random.
Yes.
There is no machining involved. You can do it at home.
So they
frankly.
go in all higgledy-piggledy with lots of space
Yeah.
between them.
Yeah. So those
Okay.
wires, though,
That's
they're
traditional.
insulated. Yeah, they are insulated. Remember, they need to be insulated.
course. Yeah.
Like there's.
And they're all running through these slots, generating that magnetic field to create the force, and which rotates.
But there are many configurations.
So what's the breakthrough that you've done?
Okay, so what we thought about this when we looked into the round wire, it has advantage of a skin effect. The battery talk, you spoke about power loss, which is I square R.
Indeed, yes.
We came to the conclusion that the resistance of the wires with their cables plays a huge role in the heat loss.
Totally. And we want to minimize heat.
We want to
in
minimize.
the core of this. That's central to
That's
efficiency.
a central to efficiency, to improving the overall performance of the motor. Now,
Great.
so traditionally, these type of wires create low skin effect. Skin effect is a negative phenomenon. It allows the current to be, when it's high, the current tends to flow only in the surface. This depends on the frequency of the current.
High frequency. So
when-
the electrons want to go around the edge of
Exactly.
not the center.
Yeah.
And it's a very weird effect.
Yeah. At low frequency, at DC, let's say direct current, that effect is completely zero. Nothing.
Yeah.
The
But
current
you do have higher frequencies.
We
in
have
the
to have,
motor, so-
as we go with the
So
speed.
the skin effect does affect.
Yeah,
first.
so you remember, we have the resistance.
Yes.
It goes almost quadratically. So this is R,
Yes.
and this is vehicle speed.
Yes.
So if we have a system that can reduce that resistance from the start,
Yes.
and it doesn't increase at the end.
And this increase in resistance with velocity is a consequence of the skin effect.
Correct. That's
because
purely
it is a
skin effect.
frequency-related effect.
Absolutely.
Right. So what the R is getting higher and higher due to skin effect, due to higher frequency at higher velocities, and therefore the I squared R is proportionately larger, which determines the power losses in
Correct.
heat.
And that what brings me to the other
Right,
type
okay,
of technology, which is
Show me.
Yeah. So if we
What do we do?
make a slot with rectangular shape,
Yes. There it is. This is the one.
it's
Yep. This is our
identical to
slot.
what we have.
Yes.
One approach is to fill this completely with one single copper bar.
Well, that's
However,
going to have 100% area utilization compared with that.
correct.
But skin effects can
A
be
skin
worse.
effect because you can't utilize this middle
There's not
area.
so much skin.
So it's got so much, so much skin effect.
So you've got a lot of copper area, which is good.
Yeah.
But you've got very little
you op-
copper skin, which is a bad thing.
If you operate at 1 mile per hour all the time, this is the
would be
perfect.
great. Yeah.
But once you go to higher
higher
speed,
frequencies, that's better.
this would be very low DCR, but it goes like this.
Like that, yes, of course.
It goes so high. So
Yeah.
if you are at 50 miles per hour or higher.
It's got a higher ratio of cross-sectional
Yeah.
area to surface area.
Correct. So what we need to do is come up with a way how to basically section these into small conductors.
Yes, yes.
At Lucid, we went much smaller conductor than conventional. But the penalty for that, when you go to smaller conductors, how you're going to connect them together? You end up with a huge number of welds because typically these are made of small hairpin wires.
Oh, these are the way they come through.
Exactly.
And you'd have to laser weld them on the end.
Exactly.
To make the circuit continuous.
So you need to
So
strip
really
them,
break those up.
join them,
Yes.
weld them, and then
Manufacturing
insulate them.
nightmare, a lot of cost and complexity.
Absolutely. The yield is very low.
And resistance in the welds.
And the resistance
Yes,
and
yes.
the reliability.
So what you've achieved here is that you've maximized the slot fill with maximum area, but you've also managed to introduce quite a significant extra circumference, which will actually reduce the skin effects. You're getting part of the advantages of that, which would help at high frequency. But in order to do that, with a conventional hairpin system, you'd have lots of extra laser welds. So what solution did you implement?
New technology called
Wow.
continuous wave winding.
This is it.
All these separate hairpins can be replaced by a single winding made with a single chop.
So this becomes that. Let me see that unwound. This is like, it's made in a loom. It's
Yeah.
almost like a weaving process. And this is continuous wave winding. And I happen to know this is a revolutionary process, and to the best of my knowledge, the only machine that does this is in the heart of our factory in Arizona, making the motors for Lucid Air. And this is all CNC controlled.
It's all CNC controlled, fully automated. Even this all fully automated.
But Emad, this is fantastic, but it doesn't quite look like that. What's the next step? Let me pass you the next exhibit.
Yeah, so basically, after it's formed,
Yes.
it's pressed, and then rolled like that, you insert it inside the stator.
So this flat thing becomes that. Yep.
And then we insert it into the core.
So this is inserted into that,
insert it,
and expand out.
Expand out, and then form it to make the winding even.
With a 72 slot CNC controlled
This is,
mandrel.
Yeah, and this is exactly that winding before it's
that
formed.
becomes that.
that.
So we've got this continuous wave of material.
Correct.
We've got incredible slot fill to get the minimum resistance because you've got the maximum surface area of copper. You've got multi-piece. How many of these elements per slot?
So we have 8 conductors.
8.
As far as I know, also we are the first one in production with 8 conductors per slot.
And so you've got no hairpin welds that you would normally see with a square element, but you still have these 24 laser welds here, 8 times 3 for the 3 phases, connection to the inverter. And we're going to look at some other examples, aren't we?
Yeah.
Very soon, and we're going to see the difference because actually the competition out there has a lot more welds. But the key here is that heat generation is the enemy of efficiency. So the first step is to reduce the heat generation at its very core. But the other thing is, we still have to extract some heat because even with this system.
Yeah.
So the closer to the source of heat generation that we can extract that heat, the better. What we don't want is for the whole system to saturate through. So here, it's this copper that generates the heat. So the worst thing we could possibly do is extract the heat from this outer surface because this entire lamination stack of magnetic steel for the stator would get heat saturated, and we'd only start extracting the heat there. We'd have a temperature gradient between the extraction point and the copper, so the copper's going to get hotter and it would have higher resistance.
Conventionally, stators are like water cooled at the surface.
Exactly.
But that's really further from the copper wire because the copper wire has insulation. It has an insulation class that goes to 100 degrees, for example, Celsius degrees.
So what was your solution?
Our solution is to bring the heat extraction very close to the copper.
And here we have it.
Yeah.
In these laminations, you can see the tiny slots.
Yeah. The tiny slots, the small slots here between 2 neighboring copper slots.
And you can see those micro channels.
Yeah. We run ATF, which is automatic transmission fluid, to extract heat from very close to the proximity of the heat.
And this is an incredible breakthrough that you pioneered, Emad, because this allows the extraction of heat really close to where the copper is. And how have we been able to do that? Doesn't this interrupt the magnetic field?
We were able to design these macro channels in a way that the magnetic field is unidirectional, so it doesn't interact. And the nice thing about a trapezoidal shape, the magnetic field is coming in the area here. We optimize that to be exactly the same.
So the flux is coming through here.
Absolutely.
And effectively, you've identified this magnetic dead zone.
Yes,
here,
this is the channel.
We're using as a micro channel. This is the breakthrough to get minimum heat generated to start with in the copper winding and to extract what heat is generated super close where everybody else is extracting heat around the circumference.
And you can see here the middle side of the core look different.
Yes. Now you see this slot that runs around the center of the stator. This here is a manifold, and this is where the cooling fluid is pumped into the system. just remind me, Imad, just again, why is it made from a series of laminations? Why
Yeah,
isn't this
you
a
know-
big block of steel? Why is it made from 400 laminations?
We spoke about skin effect
Yes,
earlier
yes.
and eddy currents. Well, briefly.
Eddy currents.
It's the eddy currents.
You want the magnetic flux to run round this way, and you want to separate the
So the
separate out.
the eddy currents
It's very
don't flow
clear
this
way. You're ensuring that there aren't axial components of eddy currents. From the right-hand rule, we've got we've got the field, we've got the force, we've got the current, and it's got to go this way around. So the force is driving that rotor around. The current is going down, axially down the slot, and the field has got to go purely in each of these laminations.
Absolutely. So the field goes around in the laminations, but we want to prevent currents flowing from one lamination to the other. Right now, we go to a thinner and thinner laminations as we progress.
And I know there's a special secret here because right at the end of these copper windings, we actually reduce the size of the slots. The effect of like when you're watering your plants with your garden hose, putting your finger on the end of the garden hose to get that spray of jet effect of cooling onto the end windings. So this is a real interesting fusion of advances in electromagnetism and advances in thermodynamics. And really to sum up, I'd like to say, remember that this magnetic field actually rotates around, and that's what drives the rotor around, which we're going to look at next. But what is not really understood is when you put your foot down on the accelerator of an electric car, what really goes on? Well, the inverter gets that signal from your foot, from the pedal, and that tells the motor to spool up, send signals to increase the speed by which that magnetic field rotates. But it's more complicated than that, because you need to draw more current in order to accelerate it at the same time.
Yeah, and this brings me, Peter, to an interesting point that I think is typically misunderstood. So let's just draw torque speed curve, the envelope that
The classic.
Yeah, this is, say, torque.
This is torque.
And this is a speed.
Right, yep.
Could be a rotor or vehicle.
Yes, indeed.
And as you know, battery of the motor, mechanical output of the motor is zero at zero speed.
Exactly. This is a common misconception.
Yeah.
Because I often hear, motor power is maximum instant at 0 RPM. No, at 0 speed, power is 0. Torque is maximum.
Absolutely. And that's why we turn off our system is, let's say, in stoplights. And because power is 0 at the wheel, even if you're generating torque, or generating force, it's still 0, no matter what.
And with 0 movement, you'd have 0 efficiency in that case.
Yes, because your output power is 0 divided by input power, which is you consume to generate, let's say, magnetic fields.
Efficiency is literally
the efficiency is
zero. So the test case thermally for the motor is at this low speed, high
low
torque.
speeds.
But the test case thermally for the battery is at the high speed, high power.
Absolutely correct. And that's why when we design our motor cooling, we have to consider that not only the high power region, it's also the low power, high torque, acceleration.
Particularly the low power.
Particularly the low power.
Yeah. So, Imad, this is fascinating.
Yeah.
I think it's time for us to look at some examples of how some other manufacturers approach their stator design.
Yeah, let's do it.
Let's go and do it. Well, let's start at this end. This looks a familiar friend.
Yeah, this is our stator production in the Lucid Air today.
Yes, yeah.
This is what we produce for all variants.
And just to summarize, we see this classic wave-wound wiring system, no laser welds on the back, just laser welds here.
And nothing here except for the terminals.
Exactly. And let's go through in a little bit more detail, because this is a cutaway of ours.
Yeah, we spoke earlier about the rectangular wire stacking. It basically maximizes copper slot fill. And you can see 8 conductors. As far as I know, we are the first in production with 8 conductors per slot.
It's almost 100% slot fill, minimize resistance, 8 elements to minimize skin effect.
Absolutely.
And we've got the close proximity of the microjets there.
Yeah.
So we get super close cooling, and we get the necking of the jet to create a spray effect on these copper windings. And crucially, these are our bus bars.
Yeah. Yeah.
fit on here?
Yeah. These bus bars, this is how long? This is the connection directly to the inverter.
So they're about 40 mil long. And remember, the shorter you can make this, the more efficiency you have. A measure of design elegance and design engineering capability is the shorter you can make that. It's almost the shorter you can make them, the better you are as an engineering
And
outfit.
applying this mentality in every detail.
Absolutely every detail.
Yeah.
Right. What have we got here, Imad?
This is their American company. This is their latest technology, Stator. It's in production with their
Mass production.
Yeah, and mass production currently in all variants
And
they
it's
have.
very different looking.
Yeah, so this is a round wire. It's a traditional way to make winding for many years now, for many decades.
Random wind.
Random wire windings stranded. We spoke earlier about its advantages and disadvantages.
And this is just like your diagram that you drew.
Yeah, it's very similar. The slot a little bit round shape to optimize more slot fill. However, you can always end up with a much less copper slot fill. Usually about 20% less than the copper slot fill.
Yeah, but you get a little bit better skin
Effect.
Yes,
Yeah,
yes.
yeah.
Now you've got what this looks like string, which is tied to
Yeah.
hold these end
Very
windings.
laborious type of lacing to get the winding together.
And I'm just thinking about tolerancy and consistency of product with this process.
So there is forming fixtures today to form the winding in
Yes,
such shape.
yes.
But yes, the end winding height is definitely larger,
So-
especially in the bottom side. You can see it's about 40 millimeters.
Exactly, and it's literally tied with string. Compared with ours, this is robotically formed. Totally CNC robotically created. And this is exactly what we're building today in our factory in Arizona.
Yeah.
And it's not just the quality, it's the consistency of the product, which is crucial. Now, the other thing I'm noticing here is these channels, presumably for cooling, right on the outside edge.
Yeah.
So the heat is generated at the copper here.
Yeah.
It has to travel all the way to the outside, saturate this entire mass, this thermal mass, compared with our smaller heat generation because we've got 100% slot fill and we've got close proximity cooling.
Yeah, much less temperature gradient. They're
But I
much
also
smaller.
noticed there is a similar feature here that this manifold for the cooling is in the same place, in the center of the stack.
Yeah, so-
but of course, the direction is very different from that manifold.
The same idea to feed the fluid from the middle.
Each way, so it's symmetrical.
It's symmetrical.
But here, from the manifold, the fluid goes right into
Right
the core.
in the
It
depth
doesn't
of-
stay on the surface like this.
Correct.
So this is a step change advance.
It's a huge change. And of course, it's all patented in-house here.
Totally.
Yeah.
And what have we got here? Another example of the same?
Yeah, this is just without the cutaway, just to show you the terminals.
Now that's fascinating. Look at the length here.
Yeah, it's much, here is...
Now,
it's
how does that compare with ours?
Yeah, it's 4 centimeters, 40 millimeter here. It's maybe 4 times bigger
So
or so.
why is that? Because the length here is the enemy of efficiency. We as design engineers strive for the elegance of this sort of
every
system.
detail matters. We want to reduce the losses and the
Yes.
heat from
Yeah.
every portion.
Yeah.
And this is, of course, a significant also a heat source.
I've seen a lot worse than that.
This is actually quite
It's
good
not too bad.
compared to
I've
many.
seen
You've
others. I've seen them that long.
That's correct.
And I think this is the shortest I've ever
Yeah,
seen.
this is a good integration.
And
yeah.
you know I drove the whole team nuts getting them this short. Do you remember that?
I remember that. Absolutely
They
remember.
were that long, and I said,
we're
"No,
thankful.
no." Do you remember?
Push for
It was
every.
like every last millimeter. So, right, so we've done the American, but I should say also, that is this the same motor that we find on the fabled tri-motor version of their car?
This is absolutely this one coming from the tri-motor.
This is the one
variant. Yeah.
So that is the very
Yeah,
latest, up-to-date technology
it is.
in the world.
Yeah,
right.
Yeah.
Now, what have we got here?
Yeah. Got here is a German sports manufacturer, Super Sport, and
With a fabled racing history.
yeah.
So if we look on this side here, we see that CNC formed, very similar sort of shape to ours, but it's not continuous. These are the hairpins slotted in.
Yeah.
And what have we got here on the top then?
We got them stripped,
Yes.
welded, and insulated.
So let me get my arithmetic right. We've got 72 slots.
Yeah.
And we've got 4 elements per slot. So you've got 4 times 72 welds. Is that 288?
Correct.
So you've got all these extra welds, and then you've got this thermal material here, which is going to hold the heat in.
Yeah, it's insulating material mainly for dielectric properties, but because it adds this layer of insulation, it also increases the thermal resistance, which reduces the heat transfer.
Right. So now, what about cooling? Because I'm not seeing any channels in
No
this.
channels here.
How is this cooled?
They used a different approach, more traditional approach,
have to have
which
something. Go on, show me.
is called cooling jacket.
Oh, so
basically,
this is water-cooled?
This is the housing of this motor.
So this goes
stator.
over this slot.
Yeah.
Goes right over it.
Goes right over it.
And here we have like a spiral here,
Yeah.
which has a water flow around that spiral. So, and this, the heat is generated at the copper. It has to go all the way through the lamination stack, and then it still doesn't get to the cooling fluid. It has to then go through
And
this.
remember, usually this
housing.
contact between the aluminum and the steel can be poor.
It can be poor,
So-
yes, because it's a very big surface
Yeah,
area
big
to
surface.
get absolutely
yeah.
tolerance correct. So, look, I think that's a fascinating overview, but the proof of the pudding is in the performance.
Yeah.
So let's weigh these and see how they stack up, shall we?
Absolutely, let's
All right,
do
let's
it.
do it, right. So, Emad, I have the scale ready.
Yeah,
Which one are we
exciting.
gonna weigh?
Let's do it. So we start with
The German super sports
super
car.
sport car, and this is the stator.
How much is that?
Yeah, so that's 23.05. So basically 23 kilograms.
23 kilograms, okay.
Yeah. So put this back and go to
And
the
next
next.
we have the American, yeah.
And this is slightly 23.85 kilos.
It's a little bit heavier than the German.
Oh, yeah, slightly. Almost the same. Maybe the bus bars make the
And
difference.
finally, the Lucid motor.
The Lucid motor. And here, 19.05. 19 kilo.
So some useful data points, but before we look at power to weight ratios, this is only part of the story, it's only half the story.
Yes.
We need to look at the full motor.
Yeah.
So really that takes us to the rotor.
Yeah, a rotor. We're going to explain some theory and then we come back to the rotor.
Let's do that.
Yeah.
Great. So, Emad, we've gone through the stator very thoroughly. We haven't even got to the part that moves yet.
Yeah.
Tell us about the rotor.
Yeah, so the rotor, of course, integral part of the motor. It is with the stator together acting at the air gap level, generating torque. And the rotor has a set of poles
Yes.
that magnetically interact with the electromagnets here in the stator.
Yes. And this is 6 poles in this case.
It's the 6 poles in the rotor and 6 poles in the stator.
So it's-
and believe it or not, the poles of the stator and rotor, they don't have to be equal, but they are usually.
Really, really?
Yeah.
So this is a 6-pole permanent magnet synchronous motor.
Correct.
And that fits just directly in there. Do you want to?
Yeah, so we can show you how we can actually...
There we have.
Yeah.
And a very narrow air gap between the two.
It's usually the air gap ranges between 0.4 to 0.8 millimeter, depending on tolerances and mechanical
And that's
structure.
crucial because to generate the torque.
It's actually crucial to have it small,
Yes.
but there is a moderate level where it can be too small for harmonics to be affecting the rotor losses.
Indeed. So I'm noticing a remarkable feature here. The rotor itself is hollow. And I remember in the early days when we were conceiving this motor, me asking you, what does the middle of a rotor do? Something that transmits torque. Doesn't that metal do virtually nothing in the middle there?
Yeah, we have 6 poles, so we have a rotor with this V shape. And if you think about...
Is the V shape for the magnets?
Yeah, so if you look at this shape here,
Yes.
so we have the 6 poles.
Yes.
And,
1, 2, 3,
and,
4,
and-
5, 6.
Yeah, and the magnetic field tends to be...
That's right. At 90 degrees.
And the
angle.
middle here, there is not much magnetic flux going through.
Indeed.
So we optimize it to remove as much steel in the middle
Yes.
And make it as a hollow shaft because the reduction...
But indeed, if there was much magnetic flux, at that reduced radius, it wouldn't have much effect upon torque.
Absolutely.
Now, I've got a great
and-
analogy here, Emad. A great classic example. We've prepared this prop shaft from a truck, and this is something that is designed to transmit torque, right? And we've cut it down the middle. And what do we see? That this prop shaft from this truck is hollow. Why is it hollow? Because the metal in the middle doesn't do much. So there's a great structural analogy here. You know, this pickup truck prop shaft, hollow center
It's
for
for
transmitted
a good
torque.
reason, right?
And it's a very similar analogy to
Magnetics,
why
yeah.
we've hollowed out the center of the rotor there. Now, this is a fascinating point because when we conceived this motor with this hollow center, it led to another innovation. What could we do with this? What could we place in the very inner core of the motor?
Yeah.
And that led to our active core breakthrough.
Yeah, and this is the shaft.
This is right the shaft in the center.
This is the shaft,
So that
which
goes right in the center
Yeah,
there,
which
right.
it goes right in the stack. This is half of the rotor, which is
Yes.
a single stack.
Yes, yes.
We'll show you later on how we insert the
And
magnets.
it's connected through these spline features.
Yeah.
And what do we put in this shaft, E-Man?
Yeah, we're putting a differential.
A micro differential.
Yeah, this is how large a differential of this motor, and you know the capability of this
It's
motor.
capable of transmitting 670 horsepower.
Yeah.
How many newton meters?
This motor is capable between 600 to 820.
800. Let me
820
go and get the rotor with this incorporated. And hang on, before I do any more, I'm going to remove my Swiss wristwatch because I don't want it in too much proximity to the highly magnetized rotor.
Yeah.
And here we see deep inside the differential housed within the rotor.
Yeah.
And how fast can they spin?
This rotor is designed up to 20,000 RPM.
It's remarkable. I've just removed my Swiss watch. It's reminiscent of a Swiss watch. It's remarkable that this can be so miniaturized. But remember, this is running at motor torque, not output torque.
Yes.
We run a 7-to-1 reduction
Yeah.
ratio, so it sees 1/7
Yeah.
of the torque that an output diff
yeah,
would
typ-
experience.
Yeah, I would usually a high torque differential is placed after the reduction.
Exactly.
Which means it requires to carry much higher torque. That means it's larger. So the intelligence here is put it in the high speed region, spin it faster, make it smaller.
And also, we have a 4-element bevel planetary set, where a conventional diff has two
Two.
elements.
Can carry more
So
torque.
again, so effectively, the load on each of these gears is 1/14 of a traditional differential. And that really is the secret to making this work, slotting this right in the very core of the rotor. And I'll cover this in more detail when we have our tech talk on transmissions later this year.
And this is again how the fusion between electromagnetics, mechanical, and thermals. But I want to explain a little bit further how the electromagnetic side of the rotor works. So here is a stack. So similar to the stator, this is made of laminations,
Indeed. And for the same reason, reducing the eddy
the
currents?
eddy currents. And the magnets are placed into these slots, these cavities. These are two sets of magnets.
Again, and they're configured at an angle which
this
puts
is-
them at 90 degrees to the lines of flux.
And this specific shape is so that the torque density is high.
And you have a very slight different angle in that
Yes.
chevron because of the way the flux flows.
You want to minimize what's called cogging torque, which basically the torque ripple in the air gap. Basically, it's great for MVH. And in order for us to increase the torque, we put these two sets of V shapes.
Yes.
That would help us increase the reluctance torque.
Now, what's really crucial here is that the edge here of these laminations has to just be strong enough, that tiny, tiny element here, strong enough to hold these magnets in with a centrifugal force. So the G-forces of these magnets is 4 times at 20,000 RPM that you'd experience at 10,000. It's a very much a quadratic relationship.
Yeah, absolutely. So another point, of course, in relation to the optimization of the rotor, we come up with a 6-pole configuration.
Yes, yes.
Because speed of the rotor is a
Yes.
function of frequency of the magnetic field.
Yes, yes.
And then 120, and then divided by the number of poles. So increasing the number of poles, that means we would reduce the speed at the same frequency.
Yes.
So the balance of getting the number of poles to be optimal for our speed and torque aspiration is key.
Absolutely.
And all these considerations were taken into account when we did our computer modeling.
It's a classic engineering compromise.
Yes, absolutely.
And we've got some little circular elements here. These are for the studs, which hold the entire lamination stack together.
So, of course, because we have two stacks, this is just a stack with the magnets already potted or glued inside.
Yes, this is why I don't want my watch near.
Yeah, this is thankfully not magnetized here.
Yeah.
And
I think I believe you.
yeah,
you never know.
Yeah, you never know with the magnets. You never trust them, seriously, because you don't know.
These are powerful magnets. I tell you.
Super powerful.
Don't
Now,
underestimate them.
yeah, so in order for us to keep these stacks in hold, of course,
Yes,
these are, this is press fit
yes,
inside,
yes.
but you need to keep them together. We have what we call the riveting system,
Exactly.
and that's
So
shown
it's
in
not
this.
bolted, it's riveted through.
It's all riveted
Yes,
here with this
yes.
balance plate. Another feature that we incorporated in this rotor is
the resolver,
the resolver.
which completes the masterpiece.
Yeah.
The resolver is just so
Who's-
beautifully integrated.
Because if you going after every millimeter,
Yes.
we couldn't find
Who'd be doing that? I can't
we
think
couldn't
it could be.
we had a restriction of the length of the motor because
Yes.
of the CV angle.
Yes,
It's
yes.
all this global optimization of the
Velocity
vehicle.
joint for
Yeah.
the drive to the
Yes.
front wheels. Yeah.
And we integrated the resolver
miniaturized.
to be in the shaft.
So this is the resolver here.
Typically, it's a separate part.
Look, the resolver lobes, the three lobes, are integrated beautifully into this shaft. It's not even an extra part.
So the resolver basically is an electromagnetic circuit to measure the position of the rotor with respect to the stator.
Yes,
Because
it's-
remember, we have two sets of poles. We have to align the rotor to the stator.
It's how the 6 poles are aligned relative to each other.
Exactly.
And it's a positional sensing device.
Exactly, because
Yes.
when we apply the
Yes.
current here, we want to know the angle of the rotor.
Totally.
So, and we have no information
And we
except
need
with
to
this.
tell the inverter this.
Yes, all goes to the brain of
The
that.
brain is the inverter.
Yes.
So the inverter takes this data and it figures out where the rotor is in space relative to the stator and what signals to send as a consequence.
Exactly, and of course, it also measures the speed, position,
Totally.
and speed.
And speed, yes, yes.
Yeah.
So I think we've done the rotor. Let's go to our array of examples and different approaches to designing rotors. We have this array behind. Let's go and take a look. So, Emad, we've got a great array of rotors, and this one, of course, is familiar, our Lucid rotor.
Yeah. So this rotor, as we said, is made of two rotor stacks, riveted together with these balance plates, and of course the shaft.
And it's super compact, super short as well.
Super compact, about 110 millimeters, one of the smallest rotors in the industry.
And 20,000 RPM up to 670
yeah,
horsepower.
yeah.
But, Emad, there is an elephant in the room. There's a much vaunted American-made rotor, which has got a carbon wrap.
Yeah.
So let's take a look at that. We happen to have one here.
Yeah, this is our carbon-wrapped rotor. The carbon wrap is mainly added for mechanical integrity of the rotor.
And this is the very one in the famous American triple motor machine.
Yeah, this is from the tri-motor machine, yeah.
Yes, yes. So let's take a deeper look at this carbon wrap and what it actually achieves. And to do that, we've got one which is cut away here. Take me through that.
Earlier, when we were speaking
Yes,
about our
yes.
stack,
Yes,
the centrifugal force
yeah.
was the driver factor for making these bridges.
So what holds them in? It's just those thin tendrils.
Then, of course, the material properties. This is electrical steel designed to meet these RPMs.
Yes.
And at this level of RPM, we have to have that optimization between the magnetic and mechanical to be very
And you can just see here just how thin those are. Now, there's a real classic engineering compromise at work here, because to get the torque, we want to put these magnets as far out as possible to generate that torque, that moment. Remember, it's force times distance.
Yeah.
We want to get them as far out as possible.
Yeah.
But we want to have just enough steel in the lamination stack to hold these in.
So basically, if by removing or by reducing that steel bridge and having a closer connection between the magnets to the stator, to the air gap, you generate more magnetic field
Yes.
and hence more torque and force and power.
And ultimately, if you took that to the limit, there wouldn't be any steel holding the magnets in, and you get this surface magnet effect, pushing the magnets right to the edge if you're really trying to get the last bit of torque from that rotor.
Absolutely. And this is the technology with this rotor.
And that's what needs that.
It needs that. If you look here,
So here we've got one cut away
and be
without-
careful, this is magnetized.
Okay.
We got to be
well,
careful.
First of all, we've got the wrap.
The
This
carbon
is
wrap.
a continuous filament round carbon wrap, slightly different
quite
from
thick and
it's
solid,
quite
very
thick and
strong.
solid. Yes, it is, and this is super strong. It's the same sort of technology that's used on tanks for hydrogen, for fuel
Yeah.
cell, to hold
That pressure.
the pressure in.
Yeah.
And it's a very similar analogy to hold the centrifugal forces in at very high
At
speed.
20,000
'Cause this is a
RPM.
20,000 RPM rotor.
yeah,
So we have a surface-mounted magnet system
Yeah, it's
here.
yeah, no, yeah. It's fascinating that this rotor is made of the lamination instead of a single, let's say, stack and lamination. This
Yeah.
is made of these
Multiple
poles.
pieces
It's
fit
similar,
in like
but
that.
they
But
have
they're quite separate.
Yeah, they
pieces.
have 6 of them.
Yes.
6 sections.
Yes.
And then the middle one, so 7 sections.
So they push the magnet so far out
Yes.
that without having this wrap, it would fly off.
Exactly, because they are not connected together.
But we've got more torque. How can we generate more torque without having to go to this? Because this is a complete pain to have to do this.
Yes, so
and very expensive.
Yeah, our rotor, generates up to 820 Newton meter. This rotor, as far as we know right now, 470 Newton meter.
So are we nearly double without having to resort?
Yeah, in order to scale that to a higher volume, it's going to be very, very, very expensive. But essentially, the technology has been there for many decades.
Totally, it's just borrowed from racing cars. Yeah, exactly.
And as we said,
This is the breakthrough to make this with higher performance, mass manufacturable, rather than having to resort to race car type technologies.
yeah, and of course, when you add that wrap, remember the air gap? We talked about the air
Yes.
gap range
Yeah,
is
exactly.
0.4 to 0.8 millimeters,
Yes.
usually the optimal. This is roughly maybe 1 millimeter adds.
Yes.
And that means, although we increase the magnetism because of this, removing these bridges, the steel bridges, you reduce your torque by other means.
That's right.
So, you know, there is compromise with this.
And interesting, this is continuous filament wound, which is a classic technology for reacting hoop stresses. But here we have a lap joint on this woven. So where we have this lap, there's a potential to influence that crucial air gap. And you see just how much extra length there is on this carbon wrap compared with the axial length of our Lucid rotor. So we have one other example here, and this is from the prestigious German sports car marque.
Yeah, it's the same family we talked about earlier,
Exactly,
the stator family. This is the rotor. It's a permanent magnet. It's 8-pole, and the reason is 8-pole. You can see the structure here,
yes.
as well as you can see it in the resolver lobes. It's a large rotor with some air-cooled buckets here, and as far as I know, it's 16,000 RPM.
This is considerably larger than the...
Considerably larger to generate higher torque, but the RPM is compromised.
Okay, this is a fascinating oversight. Now, the proof of the pudding is in the tasting.
Yeah.
So let's measure the weights.
And then
compare
measure the power, and then the power density.
Let's get the scales. So, Emad, we're set. We've got the scale, but there's one special ingredient here because these are highly magnetized.
Yeah.
Let's isolate them from the metal of the scale.
This is a steel.
Are you ready?
So.
What we got first?
Yeah, we go with this further one.
This is exciting.
So we're taking. Be careful with this.
Now, this is the premium German super sports car rotor. And what's that? 24 kilos dead. Exactly 24 kilos.
Interesting. That's
nice round number.
Yeah.
Okay, I'm glad you're doing all the work here. Keep you fit. Right, next, now we've got the premium high performance
feels lighter.
carbon wrapped American rotor. Oh, that's a lot lighter. Look, that's 16.3. That's nearly just 2/3. It's about 67% of the mass of the German rotor. 16.3 compared with the 24 kilos.
See, even with that foam, it wants to grab.
And now we get the Lucid rotor.
lighter.
And that's just 12.
And it includes the differential, portion of the differential.
I was going to say, now look, this isn't just the rotor, this includes differential. So we're not cheating here. This is, I'm not sure how much the diff weighs, but I mean, we're nearly half the weight of the premium German one here.
Yeah.
So Lucid has it so far. The next step, we've got to add the mass of the rotor and the stator. So premium German, the stator was...
So the stator of the German brand was 23 kg. The American brand was 23.8. This is stator, kg. And the Lucid stator was 19 kilos. The rotors, again, to recap, 24 kg for the German premium sports brand, and 16.3 for the American brand, and 12.4 kilos for Lucid. Combined, 47 kg for the German brand, 40.1 kg for the American brand, and 31.4 for the Lucid. And then the power, based on revealed public numbers, 350 kilowatts for the German brand per motor, and 250 kilowatt for the American leading brand, and ours is 500 kilowatt.
Hey, hang on a minute. This is 250 kilowatts.
Yeah.
And this is 500
kilowatt.
So two of these is the same power
it's
as one of these.
It's
literally a 2-to-1 ratio, despite all this very expensive carbon race technology. 2-to-1.
Yeah.
So now the bottom line is gravimetric power density.
Yeah.
By that I mean how many horsepower per kilogram for these three fine examples.
And we are including only the stator and the rotor here, but fairly doing it equally the same for the three type of motors.
Yeah.
So the power density, which is horsepower per kilogram for the German sports brand.
That's for rotor and stator combined.
Yeah. So basically, it's horsepower divided by its weight.
Yes.
And that's 10 HP per kilogram.
10 horsepower per kilogram.
10.0.
And then we go to the American technology brand.
Yes, American technology brand is 8.4.
Oh, so the Germans have it in
It's
terms
slightly
of power
higher,
to weight.
yeah.
Slightly higher
Yeah.
than the American. That's
Yeah,
surprising.
yeah.
So 10, 8.4. What's the bottom line?
This is 21.3.
Really?
Yeah, HP per kilogram.
That's unbelievable.
Yeah.
It's nearly 2.5 times that.
Yeah.
Power to weight.
Yeah, and this is without carbo wrap.
And that's including the differential.
It includes the differential.
That's amazing. Now, the fascinating thing is that the 21.3 horsepower per kilogram isn't the most exciting attribute of this. It's the efficiency, because that has a multiplier effect upon everything in the vehicle. The power to weight ratio of this unit only pertains to the unit itself, but efficiency affects the whole mass of the whole car, how far you can go with a given size battery.
Yeah.
And that's what's so crucial,
Yeah.
combining that extraordinary thermodynamic and electromagnetic efficiency with this raw horsepower per kilo, gravimetric power density.
Yeah.
Now, we've got one last little treat for viewers. Please come this way. And we've got this exquisite cutaway of our drive unit. Emad, take us through a little bit of this. It leads on to future tech talks with the inverter and the transmission.
Yeah, so, this is the integration of all components in the drive unit. It includes inverter, stator, rotor, and gearbox reduction.
And there's 2 reduction sets here.
Yeah, 2 reduction sets because the differential is embedded in the rotor, as you can see here. This is the rotor, this is the stator. So what made the system so compact and so efficient is the level of system modeling, design, and integration here.
Yeah.
It's all done in-house, and it's all developed by scientific approach.
But most of all, it's a labour of love from a huge team of brilliant engineers that I'm so proud to be leading. It's a
Brilliant,
privilege.
committed, dedicated engineers, and of course, the engineering is one side, and it's production and manufacturing is another side. And this unit is currently mass-produced, basically.
In our factory, and
in
this
our
is the
factory.
important thing, this technology is designed and developed and manufactured in-house.
Yeah, absolutely.
But I've got one more lasting comment, one final comment to make, and that is the crazy notion, is it possible to create, never mind a 74-kilogram drive unit, is the zero mass drive unit a fantasy, or is it even achievable? Come this way. So, to wrap up, I couldn't help myself but to cover this crazy concept of the zero mass drive unit. This integrated drive unit that's in production today weighs just 74 kilos. Now, if this is more efficient than a competitor, we can go a certain distance with proportionately less battery pack size. Now, if you look at the Lucid Air battery pack, if we look at the Grand Touring, we have 112 kilowatt hours of energy. And in the case of the Dream, we have 118 kilowatt hours of energy. Now, that pack, because they're the same number of cells, they both have 6,600 cells, slightly different chemistry to achieve those different energy levels. That pack weighs approximately 685 kilograms. And here's an interesting little bit of arithmetic. 74 kilos, what percentage of the 685 does 74 kilos represent? So we do 74 divided by 685, and it's roughly 11%. And in so doing, if we can achieve this 11% better efficiency, we actually effectively pay for the full 74 kilos for free if the 74 kilos become effectively zero mass in the vehicle. And that is why I prize efficiency so highly above all else. Not just because it can achieve a crazy concept of zero mass, because it's going to drive down battery size,
Absolutely.
and it's going to drive down the cost and lead to a more widespread adoption of EVs, which is our mission here at Lucid. And thanks to you and all the team, Iman, it's a pleasure.
Thank you very much, Peter. What a pleasure. Thank you very much, everyone.